us all. I hope we had a pleasant night. Today we'll be going through chapter 6 of the book. I hope you've all gone through the chapter. You've read the chapter better than I do. I haven't given it enough time as I should have, but luckily for us, this is a continuation of the previous chapter presented by Malan Shamsu, and this is a shorter version, and it's not as difficult as his own. We'll just be using some libraries, and most of the explanations here we've already covered them, but I'll be going through them quickly. So in this chapter, using neural network to fit the data, we'll be looking at nonlinear activation functions as the key difference compared to linear models. So, and then we'll be working with the Pytorch NN model, and then solving some linear fit problem with neural network. So artificial neurons. At the core of deep learning, we have neural networks. That is basically what we're talking about. Deep learning, we are talking about neural networks. So neural networks are mathematical entities capable of representing complicated functions through the composition of smaller functions. We have small chunks of functions to put all of them together into solving a very complex problem. So from the name neural networks, we all know it's, we may think of it as coming from the human brain, how the brain works, the field of neuroscience, and that's how it was inspired from the very beginning. But nowadays, modern neural network architectures have very slight resemblance with the actual workings of the neurons in our brain. So what is a neuron? It is a basic building block of these complicated functions. So what do we do? This we've been going through it many times. It's a linear transformation of input. We know what we do. We multiply our input with the weight, then we add, we add bias. So this is a linear function. Then when we multiply that by a non-linear function, which is also called our activation function. So that's what our neuron is. So we can define it we can see it using, for example, this diagram. We have our output, then we have a multiplication of the weight and our input added to the bias. So then we have a function, which is called activation function, a function that, because this will give us a linear function, then we have to make it non-linear. We use the activation function, for example, tan h. So basically, this is what a neuron is. And we can also see another example, assuming we already learned our parameters, which are learnable parameters, which are the weights and bias. We have 2 and 6. So when we have an input of 18, we'll be left with our weight, that is 2, multiplied by our input of 18, added to bias, which is 6. We have 42. Then we have other inputs. We'll have these values. So you see, this is a linear function. Then when we take a tan h of the values that we have to give us our output, then it results something like this. We can observe the values for these 3 examples. For the first one, we have 1. For the second one, we have 0.39 whatever. And for the last one, we have -1. And this is the range of a tan h from -1 to 1. So this is how the graph is. Everything has to fall between -1 and +1. Is this clear? I hope this is clear.
Yeah.
We've been talking about this since from the chapter 1.
Yeah. So I want to add something about the activation functions. Yeah, you just explained it that using these linear functions. So the reason why we don't want linear function is that linear function are simple functions, just like you see w times x plus b, which is just linear, like linear, simple linear that we saw in the last chapter, maybe linear regression, something like that. These are simple models that they cannot learn something very complex. So to make our model learn very complex relationship, then we need to use some kind of nonlinear functions, which are called activation functions that act on these linear function. So the reason why also these activation functions, they are also differentiable in the sense that we can actually back propagate to try to find the derivative of those of the loss function with respect to this weight W and B. So this is one of the essence. All these activation functions, they are differentiable in some way. Yeah. Thank you.
Thank you for that. I'll come into a bit more of them shortly, but yeah, thank you very much for that. Anybody want to add anything? Idris, or I see Dr. BSB is also here. Or we should just move on. So we have a multi-layer network. Generally, we have our neural networks are not composed of only one layer. This is, we're explaining the workings of a single layer of a neuron. So we have a multi-layer neural network. It is made of a composition of functions like those we just covered. So we have our input denoted as x1, for example. Then it's a function of our weight, our initial weight multiplied by this input plus the bias. So how it works is a multi-layer. The output of this, you see this is x1, will be passed to the next layer as input, like that, up to the last layer. And then if I don't know if that is clear. So how it works, the multi-layer, instead of passing directly from the input, one layer, what you've seen here, then output, no, the output of the preceding layer will be passed to the next layer continuously until we go to our output layer. So the output layer of the neurons is used as an input of the layer, of the following layer. And then we also have to remember, as we've discussed several times, that our weight is a matrix and X is a vector. So using this vector, we can have matrix multiplication. Using vector, then we want to hold the entire neurons instead of just one. Doing it one at a time, we do matrix multiplication. So this is an illustration of what I've said. We have our output is equal to the summation or the passage of all our neurons over the layers to the end. So we have our input, then we have our layer already learned. Then when we pass the activation function, we make it into nonlinear. So this goes on after each stage activation function until we go to our output. Before I pass, Malachus, do you want to add anything here?
No, I'm okay.
Okay. So coming back to the activation function. The activation function plays two roles. Malachus has explained to them, the two of them briefly. First, it allows the output function to have different slopes at different values. This is representing the linearity of the model. So it's more powerful than just a simple linear function, as we have seen. So, and the second one is the last layer is concentration of output of the preceding layer into a given range. So what this means is our output, we have our input, then we have our output. So generally what we do is at our output, based on its value, we determine what it is. For example, we are trying to predict cat and dog. So we may decide to have a threshold that after this threshold, it's a dog. After this, maybe it's a cat or thereabout. So if we did not use activation function, we'll just be multiplying matrix multiplication. We may have values that are very, very large or values that are very, very small. So it becomes very difficult, very, very difficult to determine what our threshold is, because no matter what value you put, you may have something that exceeds that or falls below that. So, but when we take our activation function, it constrains our output, what we have in our output, to a specific range. That's what happens when we take tan h. It constrains our output to between -1 and 1. So this we can easily define. It's easy for us to define. From anything close to 1, we can say it's a cat. Anything that falls below, it's not, it's definitely not. And something in between, maybe something that resembles that. I will have example, I suppose. For example, if we are trying to classify a dog, so anything that falls very close to 1 may be the dog. And then if we have a picture of, let's say, a house, that definitely does not look like a dog. So it would have a value, let's say, very low, closer to -1. Then if we have, let's say, a goat that somewhat looks like a dog, it will have values maybe closer to the 0 or thereabout, in between. I don't know if this makes any sense. Does it? Okay, so this is the example. Does it make sense what I said? So matrix multiplication can easily result in a large activation variation of numbers that may be difficult to define, if it's good score or a bad score. So we need to firmly constrain the output of our linear operation to a specific range. Yeah. Activation functions provide this constraint. Popular activation functions include tan h, hat tan h, sigmoid, ReLU, and all of them. And similar to what I have explained, if we are trying to predict a dog, so anything closer to this value to the positive side, it's a dog. We can easily classify it as a dog, predict it as a dog, but like this car, it doesn't look like a dog anyway, so it will fall that, and then ABR somewhat looks like a dog. Does anybody want to add anything? Lately, we've been having challenges with network for Airtel users, so I want you to confirm if anybody can hear me. I'm not talking to myself. Can you hear me?
Yes, yes, we can hear you.
Yes.
Okay, okay. Because it seems a bit quiet, and I'm wondering if anybody is hearing me at all. So this is example of popular or common and not so common activation functions: tan h, hat tan h, sigmoid, soft plus ReLU, and thereabout. We can read more about them. So
can you go a little bit up? I see some statement there up a little bit up. Okay, yeah. Activation. Okay, popular activation functions include. Okay, right. I didn't see ReLU here, but it's also popular nowadays. Yeah.
Okay. That's all you want to add? More information?
No, I don't have anything to add. No.
Yeah, it's there is no hard or fixed rule to decide which activation function to choose, but some important points are all activation functions are not linear. So repeated applications of this without activation function results in a function of the same linear. If we continue doing this without any activation function to make it not linear, we'll still have the same function that is basically, the values may change, but it's generally also linear. So nonlinearity allows the overall network to approximate more complex functions. I've said this, management has also iterated. The nonlinearity, it doesn't have to fix the data only on one specific line, one linear line. So it's more powerful, and it allows us to approximate more complex functions. So are differentiable. We can differentiate them, so we can backpropagate. Management has also explained this. Activation functions are differentiable, so gradients can be computed through them. And then they also have point continuities. So without these characteristics, the network either falls back to build linear model or becomes difficult to train. So without these point discontinuities, we may easily, our linear function may easily become a linear function. But because they have the point discontinuities, that's not the case. So, and we have some points that are true for all, some important properties of activation functions. they have at least one sensitive range, where non-trivial changes in the output will result in a corresponding. What this means is that all these activation functions, they have a range that the moment you change your input, your output will also definitely change. Not that, so they definitely have that. We have this point and we have this point. This is different. So the moment you change your output, it will determine what happens. You change your input, it will determine your output will also change. So they need to have that. So they cannot be on a straight line, or yeah, they cannot be on a straight line. For example, even this, we have this point and this point that determines that. So they have at least one sensitive range where non-trivial changes in the input will result in corresponding non-trivial change to output. This is needed for training. Otherwise, then we cannot know what is happening. If changing your input does not affect your output, then you can't learn anything. And then most of them, or many of them, have insensitive saturated range where changes in the output. So, and then they have this kind of places that in this kind of locations, if you change your input, the change in the output will not be that significant. It falls within this range, but not all of them have this property. And then the activation, all activation functions have this. So then the activation functions will have at least one of these. The lower bound that is approached or met as the input goes negatively infinity. The lower bound that is approached or met as the input goes negatively infinity. So this is the lower bound. We reach it when it goes to infinity, meaning that if we don't have this point, this bound, it may continue going down, down, down up to that. So we have this bound, or the upper one is similar but inverse to the upper bound, and then that is the upper bound here. If we do not restrict it, we continue going up. Does anybody want to add anything here about the characteristics of activation functions? So what are we seeing in essence? All results in a pretty powerful mechanism when different inputs are presented to the network. Different units will respond to different ranges of the inputs, on the same inputs. The error associated with these inputs will primarily affect the neurons operating in the sensitive range, leaving other units more or less unaffected by the learning process. So generally, this is what we have for this chapter. Then we'll go. Does anybody want anything, have anything to add? The next thing we are covering is the working with the Pytorch neural NN module that we'll see in the code. Malam Shamsu?
We are good. We are good.
Okay.
For me, I'm good.
Okay. So most of these things will be seen is from the previous. The same with the previous. With the previous notebook that Malam Shamsu presented. So this we import our statement, and this we set the options for our print. So we also know that this we are just defining array, two arrays, 1 and 2, and then we have to change them to tensor, and then use this on squeeze, these functions, to make them into because it is in one dimensional, to make it into a matrix form so that we can use it in our computation. So we may see what happens. Let me see if I can. Okay. We are printing the shape of this tensor and this tensor. So if we print the size of this is just 11, one dimension. But then when we use the unsqueeze, then we have a dimension of 11. This is in this direction, like row, but then it changes it to matrix of 1 column. Then we can use it for matrix multiplication. This we cannot use it in that regard.
So what it means here is like in later we will need to use this TC and TU, for their shape here will not be compatible, right? So we use this function on squeeze and put 1. So it has an argument 1. It means put it at the circle, right? If we have 0, it will have a shape of 0, 11, right? But when we have 1, that is why we have 11 and 1. Is that correct?
Yes.
Okay.
So what we are doing here is we are defining or splitting our, we know generally in machine learning, we split our data into training and validation. So this is what we are doing. We are taking N of validation as this. We are talking about the index of our data, because with arrays or the tensors, we work with arrays with indexes. So here we are talking about the indexes, 20% of the sample, because this takes, this N samples takes the number of our samples. Then here we are taking 20% of that. So here we just shuffle our indexes. So then we see our training indices. The indices is from a specific value. We know how we categorize this, from this N val, from the beginning to N val. And then that is for training. And then for the validation is from the N val to the end. And then it returns that. So when we print this, what we have is, we have the first one for our training. This is not the actual values. We can see it's not these values that we have. It's just their index, their position. So, and this is for the validation. So it's the index. What is at index 8 and what is at index 10. So what we do here, I think all this is past, malicious, we've explained on this, right? What we do here is we assign values to the actual values from based on the indexes. So here we have TU train and TC train. So we attach the actual values, not the indexes, the actual values based on our index. So all this is housekeeping. This is where we start.
So yeah, I think this is just like they are trying to do it mechanically the hardest way. So just like using like scikit-learn that does like that we call it to create create train split set some whatsoever using a single function in sklearn. So that's what they are trying to do. They are trying to create train set and validation set, but they are trying using Python stuff. It is easier. One, you don't need to use this. It is easier to call your scikit-learn function to create something like that. The only thing that is something useful is the last one, where they use 0.1 times TU train, 0.1 times TU val, which basically try to normalize the input, right? The content. So this is normalization. But the other thing is just like doing the train test split, yeah.
So this is the NN model that we look at. The constructor for the NL.linear will start with linear, with linear that accepts 3 arguments. Actually, here we've seen only 2. The number of inputs, that is our model will have 1 input. The number of outputs, 1 output, and then whether the linear model includes a bias or not. By default, it's true. So if we don't define it, it takes the default. That is true. So when we fit our model with our validation, we have this value for our weight and for our bias, and then it's always returned that let's run it and see again. Yeah. So we have our value for our weight and the value for our bias. So we have an instance of the NN linear with 1 output and 1 input, for instance, that only requires 1 input, 1 weight and 1 bias. So if we check the weight of our linear model, of this model that we placed, we have it as a tensor this, and this needs to be true. requires grad true for us to be able to do backpropagation. It's only false at the end when we want to pass to our output, then requires grad no, will be false. So then when we check the bias, the parameter we have is a tensor of this value and also requires grad.
Yeah, so
okay.
Can you go a little bit up, Dr. Ibrahim?
Okay.
So here we train a model, right? So we want to do like a linear. So we have NN, the linear, we call it, and its argument are basically like the input side and output side, which are 1, 1 here. And now we said, okay, linear model T on val. On val is the validation set, right?
Yes, here.
Okay, yeah, right. So, yeah. So when we have the model here, when we say linear model is called NN the linear, this linear model, you know, in the previous session, we actually initialize our weight and bias, right? We give weight and we give bias. So this means that this model that we created, linear model is called NN, it automatically create or calculate our bias and weight. So that's why when we said linear model that weight, which is a kind of parameter, or yeah, a kind of parameter with this object that this object we create a linear model, it has like a parameter weight, so it will give us the weight parameter for the model. When we have linear model that bias, it will give us the bias. So if you remember in the previous session, we need to initialize the weight and bias. But this one, as you create the model, it automatically calculate the weight and bias. But how does it calculate weight and bias is something that the book didn't talk about. Yeah, so there is a formula. In fact, it's not something that it just comes. So there is a particular formula that comes given the input side and output side. It calculates the this weight and bias. Yeah, in some ways. I can share something in the channel chat so that we can see how they automatically calculate the weight and bias given the input here like this one. Yeah, thank you.
Yeah, thank you very much for the addition. So this we are just trying to create a tensor of ones, but we then we print, we can see it here. But generally we don't, and then we pass our model over it. That's why we have this. But generally we don't. Generally we don't do that. Okay, we create an input of tensor of size B. 1, 2. This is size. How many of they? And then multiply by the number of input features, where B is the size of the batch. How many do you want to add or create or import? And then L is the number of input features. The example we've been seeing, it has only one input feature. Is it temperature or whatever? But we may have a model that takes 2 inputs and maybe we present 2 outputs, 1 output, or any number of output. So this is the batch size, and this is the number of input feature. So when we create this tensor 10, so we'll have 10. We pass it through the model. We have we'll have 10 of them, and the same thing because all of it's they are all ones. So whatever happens to the model will be the same. Bala Shamsu, do you want to add anything?
No.
Okay. So now we are going. Last week managers has already created a linear function from the scratch, and they are about. So if you are replacing that the linear model 1, 1 to a non-linear one, this is how we do it. This is our linear model. And then the linear, this is how we do it. 1 input, 1 output, and our accept bias is true. Then we have to define our optimizer. This one is stochastic gradient descent, right?
Yes, vanilla stochastic gradient descent. Yeah.
Yeah. So this is our define our optimizer. And then we don't have to define our parameters, just linear model that parameters, and then we define our learning rates. This that parameters will automatically supply all the parameters that's needed in the model.
Yeah, so you can see here we have linear model, the parameters. So this is a function more or less where we call linear model that weight. It gives us a parameter weight, linear model that bias. But when we call parameters, it will not return like only, it will both the two, right? Weight and bias, they are parameters. Now this function will return both the weight and bias. Yeah, so
yes.
That.
When we list, for example, what Malachas has said, when you use this function lists linear model the parameters, it will print the
okay.
Yeah.
Okay,
yeah, this is
so also this one, when we say linear model is supposed to end the linear, this is what we are doing in that forward propagation, right? So this is forward and the linear, this is forward, trying to make a prediction, creating the model, given the input. So linear and the linear 1 it makes a forward propagation, forward path, right? Now the next thing after you do linear forward, what do you need to do? You need to do backward, right? So backward is thanks to optimizer. Optimizer is a way that implement those kind of back propagation. So everything you're gonna do in Pytorch has been implemented. I mean, back propagation, you know, all those things whatsoever. So you don't need to do any calculation. So optimizers, they are the one now that implement back propagation. So in a nutshell, if you want to do forward path, just call your linear or convolutional network or whatsoever, or put those forward. Now, when you want to do back propagate, now you just call optimizer and provide parameters. It will just do the backward propagation for you. So easy, right? Yeah, thank you.
So easy, right? So
ba kamar yadda muka gani ba ranar da na yi misali, we were doing manually to calculate the derivative, you know, which is somehow confusing, right? So we just call something like a magic.
So we have to define our training loop. So this is the function. This also you can maybe in next chapter we have a shorter way to do this, but for now this is the function, and then it takes as arguments the number of epoch, the optimizer, the kind of model, the loss function, and then your training and validation sets. So then we because we know what epoch is. Epoch is one complete cycle, right? So we have to loop through the functions we have through the entire number of epochs that we have. So for our training, we have this TP train is equals to model. This TU train is our training data. So the model is now passed in instead of individual parameters. We pass our entire model. The model will also contain, sorry, please. The model will also contain all our parameters and everything. So instead of passing individual parameters one by one, we just pass our entire model. So here we are just calling our, so this is for training. This is training loss. We call our loss function. It also have two parameters, TP train and TC train, and we know what we do, we subtract them. So this is the same with that. This is for training. And then here we have for validation. We just pass our model with the validation data. And then we calculate the loss of the validation loss. And then for in Pytorch, we have to zero, anytime we have to zero our gradient, otherwise it will just, we have to make it zero, otherwise it will just continue. Malicious, do you want to add anything please on this optimizer zero grad?
Yeah, so this is basically we know while we are doing the training, we do epoch, right? Meaning we go back from one pass, complete epoch, we go back, right? So in any epoch, we calculate the gradient, right? But if we want to come back to the next, if we don't actually zero the gradient from the previous, we will accumulate. That is sort of gradient accumulation, right? So we don't want to do gradient accumulation. We want to, at each epoch, we have a fresh gradient that we will determine which path we go, right? So that's the essence where here is called the optimizer zero the grad. It zero the previous gradient, and now you go to the fresh and calculate, to the next one. Yeah, I think that's what they say.
Yeah, that's okay. We have to zero it anytime, otherwise it will just build on the previous value we have. So just what we are doing here is we will print the first epoch, and then we'll print every 1,000, every epoch that is divisible by 1,000. If it's a modular operation, so we'll print 1,000, 2,000, 3,000 like that to 4 decimal places. So here we are calling our we are defining our linear model. It's called linear percentage values. That is linear model. We are defining it. We called it here. This is our optimizer here, and then our optimizer is, we use the SDD, and then we just pass our linear model with parameters and define our line rate. So that's what we do. This, we have our linear model. So this linear model, the parameters will just pass the parameters to the optimizer, and then we define the line rates. So and the other parameters that we need, it's all defined here. Number of epochs, 3,000. Optimizer, this is our optimizer. The model, the loss function is mean squared error loss. I think last week you managed you calculated manually, right?
Oh yeah, I think is it last week manually, right? So neural NN model also come with the loss functions that you don't need to. You remember we call like manually x minus sy square, something like that. So you can see Pytorch actually save us from those hurdles. You can manually just call the loss error. You have the implemented tons of loss, so you just know which kind of loss you want to use, and you just call it. Now, can you put like delete that MSC loss and just put NN dot? Just put NN dot.
Okay,
yes.
So that we can see.
Yes. No, yeah, so you can see, I mean, a ton of, because they are under NN, yeah.
All of them are under NN, so it will be very difficult.
So you see them, so, but there are some ones you can see them lost.
There will be, I believe that there will be root mean, no root mean squared error. We can just, it's easy to just Google the ones we have. This one we use is MSE loss, right?
Yeah, so here you can see when you put the loss, can you go over, when you put a loss, you can see many loss functions come in as well. Can you delete? Yeah, so type loss again, just loss, and then the loss. Yeah, you can see them, Hoover loss, Hoover loss, L1 loss, so there are many loss functions, but yeah, the one we do, I think, is is the default. Yeah.
So automatically we don't have to do it manually, and this is just our training, validation, and all of them. So let's run this. I hope everything works. So as we have seen, it will print our, based on this, it will print our first epoch and the training loss of this and the validation loss of this. So we can see the variation of this. This is just 92 and this is 145. Then after 1,000, we have 2 and 7 not very far apart. Then we can see after the 2000 epoch, we have 2. So this one did not change so much. And the variation is thereabout, and then 5, and then the 3000, which we define number of echoes as 3000, is this one did not change also. So, and this one also have not changed significantly. So probably we, even if we add more epochs, we will not see significant difference or very big difference. Then finally we have this. This is not even important. I don't know what's here. The print linear model, the weight and the bias. It will just print our weight and the bias. I hope this is clear. So what we've done here, we call many functions at different places and the rest. We have what we call sequential module in Pytorch. The knowledge provides us with a simple way to concatenate, to put together all the modules we need for training deep learning in one place. So neural network provides, NN provides a simple way to concatenate modules through the NN, the sequential container. So using this, we can put all our arguments, all our modules that we need. So that's all the end result. The end results in a model that takes inputs by first module as argument, takes input. So the first module is input, pass through the intermediate output models, and produces output root one. So in one sequential container, this we can pass whatever we have. So this is how it's done. For example, we take this sec model is equals to, and then the sequential. So we pass our linear model with its inputs. Okay. That is 1 input and 13 output. Then we pass our hidden layer, or what happens behind the scene, the activations. Then the last, we output our output layer. That is, it have 13 input and then 1 output. So, and we can see that this have to be the same, because after the input, then whatever we have as output has to be the input of our last layer. So when we write this to see what our sequential model is, we have linear number of features 1 for the first one, number of the features 13, and it has bias. So the second one is just tan h. And then for our output layer, we have number of input features 13, output features 1, and also have a bias. I don't know if anybody want to add anything based on this sequential and the motive behind whatever. I believe I explained, but if anybody want to add anything, we can go on. Idris, today you've been quiet. Okay.
So yeah, so this 13 we have, what brings it? What is it, the hidden layer, or is it the, what is it? Is it the hidden layer? Is hidden layer or what? Right. So here, as you said, in the linear 1, 13, we know because we have a single input, right? And it's shape of what, right? And the 13, what is the 13? So it is like we have a single input and we have 13 hidden units. And now we know the output of the layer must be the input of the next layer, which is the last one, linear as well, which we have the input is 13. So if 13 is the hidden unit, we have 13 hidden units. Is that correct?
No, we have 1 hidden unit, but the, let me, okay. Where is, I think I cannot see the top of my, okay. Okay. We generally have, in essence, what we can see is
Doctor, internet ɗinka ya tafi.
The output of the input layer is 13. Not we have 13 hidden layers. My network is unstable. I don't know if you can hear me.
Yes, we can hear you now. We can hear you now.
Okay. Do you understand what I mean?
Yes. Dama abin da yake so ka yi bayanin mana mu ji.
Okay. Okay, can we proceed? Yes. So here we're just printing based on their name of the parameters that we have. Here we print the parameters and the nature. So we can see we have for the input. I don't understand what happens here. Malicious, what happens here?
Yeah, so here what happens is like so this is what do you call it? For parameter in this model, it returns the parameter shape. So parameter shape is, we can see here is 13.1, right? We have 13, which is the activation function. Then we have 113. Then we have the last one, which will be the output of size 1. Yeah. So here it just like it print the name and also the param shape. So yeah, so the name will be here, the weight, and now you can see.
Yeah, sorry, this is the bias actually.
Yeah.
True. This is the bias. I forgot about it. That's why it confused me. That's why it's better to print this way so you can see what happens. So we have the weight, and it has this 13 whatever. We have our bias of 13, then weights of our output 1 and 13, then the bias of the output, which is also 1. It has to be 1 at the end. Okay.
So yeah, so here you can see the weight now is of size 13.1, but the bias is only 13. Can you say something about that? Also, the second on weight is 113 and bias is 1. Can you see at different level we have different weight and different bias, right?
Let me see if I can have any diagram here that it's easier to explain. Okay, I don't have. So what happens here is okay. What happens here is for our input, we have 1, then the output is 13. So we have only 1 13. For our bias, we add our bias to this, all the 13 output that we have of that layer. So our bias has to correspond with the number of outputs of that layer. That's why we have 13. But for the output, for the last layer that will give us our output, it's that it has only 1 output, a single one. So its bias will also be 1 because the bias corresponds with the output. I don't know if that is the explanation that you want me to make.
The size of weight is also 13. The shape is 13 and 1, right?
Yes.
So what is the explanation for this, the size of this shape? Why the shape is 13 and 1, the weight?
I don't understand. Just go and explain if you understand.
No, Gary, kawai ina tunani ne ban yanzu nake reasoning ne ban karanta wajen ba, so yanzu nake reasoning, so shi ne nake, yeah, I don't know.
Based on my understanding, the weight is for
the shape na, I don't know, like can you scroll a bit up a bit? Yeah, okay. So we can see like the linear is like 1:3, right? I think a chapter and they made mention some of this, I forget it, like the shape of your input and the corresponding shape of the bias, of the weight and bias. I cannot actually remember, but this is something, maybe you can continue, we can discuss it. Maybe I will open and try and see what happens. You can continue so that we
Okay, I hope my internet doesn't go off. It's showing I don't have internet. I'm surprised how I'm talking and you're hearing. So this is also just one layer. We can define the layers so that we give them a specific name, a sequential model, whatever, instead of what we did here. Just use the by the linear dot and hit.
Dr. Ibrahim, da akwai wani link da na sharing. Da ka iya buɗe mana shi mu gani a browser ɗinka ko kuma na sharing. Explaining ɗin wannan abin yake yanzu da na buɗe shi na ga.
Am I sharing?
You are sharing your computer, your browser ɗinka ba, VS Code.
Oh, then I have to stop sharing and share again. I
okay,
think
yes.
You just share the screen, your screen. Let me stop.
Okay. Right. So let me share the screen. Kuna ganin screen ɗina?
Yeah.
Okay.
Yes.
So you can see this is the linear, right? This is the linear, right? You have input features, output features, right? So this is the input features, this is the output features, bias, and yeah, right? We have the input features. So this is the shape of the our weight, right? So we can see this is the weight. It should be the output features and input features. From abunda ka rubuta output features 13 ne ko, input features 1. So that is why we have 13 and 1. Can you see that? And this is the, I made mention that there is a formula to calculate the weight, right? So the values of the weight are initialized from this range, right? Minus this, where k is 1 over input features. This is how the linear model calculates our weight. Also the bias, it should be of the shape, where the shape, okay, the shape is only output features. So the first shape of bias, it will be output feature only, only one. And also it is value is initialized from this formula where we have k is equals to, so this is what I wanted. You can continue, Doctor.
Okay. I've seen so many faces, but nobody is talking. Okay, so
please, if you want to ask question, ask. It's through this question that we understand more better. It's just like discussion. Continue, Doctor.
Yeah, we just define our the models and the whatever. It's the same, but here we just give so that we know what's happened. Here we see hidden linear, hidden activation, output layer. So when we print our sequential model, we have hidden layer that it will show us the content. Okay, here the values are changed 1, 8, whatever, but the order is the same. If we have 1 input, 8 output, then here the last layer we need to have 8 as input and 1 whatever. So and here is still the same. Hidden layer. This one, the hidden layer that waits. This hidden layer is just what we write here. Whatever we write, it changes. With our previous sequential model, we didn't do that. We just pass the models directly into it. And then we have, we can also use our sequential model output to see our bias. It will print our bias. Very small number, 0.09999. Okay. Then this, we are just running our model again. We define our optimizer here. Then when we run our training loop, defining the parameters, we have number of epochs, optimizer, it's here. This is the same functions as the one we've previously seen. The only difference is what? Number of epochs, and I think that's all. And then we print it, so we have values at epoch 1. So this towards the end at 4,000 epoch and 5,000, there is no much difference between the training loss. But then for the validation, there is a difference, but it goes on, it goes down. I don't know whether that means it has learned anything or not. So, but this is our model. And as far as the chapter is concerned, this is what we do in our model. The last part is we are trying to compare we are just plotting, comparing our linear model with the neural network model, with the non-linear model. So this is just the normal matplotlib library we use to plot the values that we have. So at the end, we have exercises that I haven't looked at. If anybody looked at, or if there is need, we may discuss them now with somebody. But just this is what we our linear model, and we can see that it's better fit on the line. So anybody want to add anything?
Is it the end of the session?
Yes.
Okay. So yeah, I don't have anything, but what I want to say is something that I read in the book and that you skip, you didn't talk about it, is universal, where they said neural networks are universal functions, right? So they said what makes deep neural networks so attractive, because like previously we were using machine learning, everything, right? But what makes it so attractive now that now people are doing deep neural network? The simple reason is that deep neural network are what we call universal approximator. So normally, if you want to train your machine learning model previously, you need to make assumption maybe if it is linear, if it is quadratic, right? If the shape of the data set, you need to choose your machine learning algorithm. But with deep neural network, it is what we call universal approximator. It's made any function. So here what it's saying is that given any functions, no matter what the shape of those features, neural network can approximate that function very well, giving the right input and output. So this is just what I want to say, like about the universality of a neural network. You may encounter it somewhere else. They will say neural network function are universal functions. So when they say they are universal, it means they are functions that can estimate everything. So that's why, for example, if you want to do machine translation, you do neural network. If you want to do image recognition, you use a neural network. If you want to use sentiment analysis, you use neural network. If you want to detect cancer, you use neural network. Everything. So they are universal approximator. They approximate any problem. They can solve any problem. So yeah, because we all know that this deep learning is not like they are solving the problem accurately. They are just trying to approximate, right? So neural network, they are universal approximator functions. So yeah. I don't know if you want to say more about that, Dr. Ibrahim, if you want to add.
No, the yeah, no.
Okay,
So,
anyone want to add something?
What do we talk about?
Megachi?
What do we may have some time so we can talk on other things.
Oh, okay. Yeah. So next week, this week on Saturday, Dr. Idris will give us take us through the next chapter. That is chapter 7. And on Sunday we have our normal week house NLP meeting. I don't know if anyone here is happy to talk to us about his work. If you are happy to talk to us about your work, you can just message me so that we can plan to do that. Just it's not something. Yeah. So that's about that. We now have 2 more chapters to finish this book. What I mean by that is that we have chapter 7. Idris will do. I will do chapter 8. It means we complete the foundation of Pytorch, meaning that we can do any other task. We were feeling like the chapter 10, 11, and of the book, they were using image, they are related to computer vision, but we are not computer vision people. So it's better for us to choose something that relates to our work, like maybe NLP, that they use Pytorch. So we'll see what will happen when we finish, but our plan also to go through this summer curricula. So we'll see what will happen. But one thing we should do is that at the end of this session, we will have like a project session. Now, this is something we'll create, project session. So the project session is this. Now we get the background of Pytorch. Now in the project session, one of us or any one of us will come and prepare a project. So I prepare a project using, I have a project that for sentiment analysis, for example, and head speech, like 4 projects or 5. They are complete project, end-to-end project, meaning you can just take them off the shelf to do head speech detection, to do machine learning, to do sentiment analysis. So like I have 4 projects. So we will have a project session whereby we'll come and do project from one end to end to see how we can actually do what we learn. But this is separate from our normal. So this is something that we can organize, that can we have time, anyone that is interested, we can come over. So also Idris, maybe I will ask him, because he's doing machine translation, he has maybe some kind of code that will take us from the beginning, given a data set, how can you do machine translation? So we'll have like 1 hour or 2 hours, maybe this is called project session, where we will be showing projects end to end, how you can do some of this stuff. Dr. Brian also, if can also do that. Yeah, so Idris, are you good with this, doing like project session where we can, because some of our colleagues here may see, oh, now we have the background, now let's see how we can do project. Yeah, do you think it's a good idea? For me, I can do that.
It's an excellent idea. I have a lot of methods that we can explore.
Yes.
So it's a good idea.
Okay, Dr. Brian, what about you? Do you think it's a good idea?
Yeah, it's a good idea.
Yeah, so yeah, cool. So the main idea is just to help all of us that are in this stuff, just to see, we share our idea, we share our, so I think the best way to learn and the best way is to try to impact and see us all grow together. So we'll arrange how to do that, but now we need to finish these 2 chapters, next chapter, and yeah, we can give me anyone with anything or we want to add.
Regarding our